So, hi everyone, good afternoon. Tom Goldstein is our first speaker in our afternoon session. Tom is our associate professor of machine learning in the Department of Computer Science at University of Maryland. His research lies at the intersection of machine learning and optimization and focuses on safety and security for autonomous systems. He works at the boundary between theory and practice, leveraging mathematical foundations, complex models, and efficient hardware to build practical high-performance systems. Professor Goldstein completed his PhD degree in mathematics at UCLA and was a research scientist at Rice University and Stanford University. Tom, the floor is yours. You can share your screen now.
All right, thank you.
Thanks.
Okay, just quick audio and video check. You can see and hear, I hope.
Yeah, everything works great.
Okay, great. And if there's any questions or anything you think I should address while I'm speaking, feel free to interrupt me. Okay, all right. So thank you very much for having me. I am Tom Goldstein. I'm going to talk to you a bit about poisoning attacks on computer vision models. And there's a bunch of different things that I would like to be able to talk about. First, I'm just going to introduce what poisoning attacks are. I'll give you sort of an overview of what's out there, and then we'll sort of focus down on some particular types of attacks that I think are interesting. Okay, so poisoning attacks are a little different than conventional adversarial attacks. Most adversarial attacks happen at test times. You have a model that's already trained, and then after the model is deployed, you want to create some sort of attack that will subvert the efficacy of the model. But poisoning attacks are training time attacks. So instead of manipulating testing data, you will manipulate training data, or in some situations, you manipulate both. And one of the things you might wonder is it actually realistic to think that your training data could be manipulated? It seems like if you allow an adversary to control your training data, then they could make your model do all sorts of things. But it turns out that there's a lot of situations where you do give the outside world access to your training data. And in particular, I think this happens a lot when you scrape things from the web. So a lot of computer vision systems are trained with images that are just scraped from the internet using bots, oftentimes with very little human supervision. And in those situations, you don't necessarily know whose data, whose hands your data has been in. And there are other situations where you might even allow people to submit things to your system. For example, if you're harvesting system inputs, you have something like a spam detector where anyone can send emails to your organization and they get scraped and put into the training data set for updating your detector. You're basically giving anybody the ability to pick and choose what ends up in your training set. And then there's also situations where you might just have bad actors or inside agents that want to manipulate your data in some sort of a way that elicits bad behaviors. So the landscape of poisoning attacks is huge, and I just in this time period, I just don't have time to talk about everything. So I thought I would just mention some of the really cool stuff out there that I'm not going to talk about. But a lot of the original work on poisoning attack is actually on regression models. I'm going to focus on neural network models in my talk, but there's still a lot of ongoing work on regression models. So, you know, how do you poison SVMs? How do you poison logistic regressions? How do you poison random forests, nearest neighbor classifiers? A lot of work done on classical models. There's also been a lot of work done on label flipping attacks. So if you have control of the labeling function, then you could take, for example, images and stick them into a data set with the wrong label. And that might seem like a very strong threat model, but that's actually realistic in certain situations. For example, in federated learning, where you're relying on a distributed cloud of agents to send gradient updates to a central server, you don't actually have any control over the data that's being generated in the model updates being produced by those agents. And so in the federated learning setting, I think these kinds of attacks are really interesting. In the cryptography and theory community, there's been a lot of work on what's called p-tampering, which basically just means online data poisoning. So data poisoning for online systems. There's some great theoretical results on this. There's just a selection of papers, by the way. I'm not trying to give a comprehensive list of all the work in these areas. And then there's a lot of works that are really just focusing down on this federated learning model, looking at things, for example, poisoning model updates, doing other kinds of poisoning attacks that only exist within a federated learning framework. I'm not going to get to talk about all of these things just because of time limitations, but I wanted to make sure that I at least pointed them out because I think these are really important. There's a lot of really important work being done in the poisoning community in these areas, both in attacks and defenses. If you are interested in reading about these things, I am going to shamelessly promote this recent review article. It was a big team project with a number of people, some of which are organizers for this workshop, but data set security for machine learning, data poisoning, backdoor attacks, and defenses. And we just review a whole bunch of the poisoning literature, including more historical literature and classical methods and things that are going on now for a wide range of models, not just neural networks, including the federated learning case. So in this talk, because I don't have infinite time, I'm going to just pick a few things that I find to be particularly interesting and that we work on in my lab, and I'll try to tell you a bit about them and make sure I point out related things that are going on in the community when I can. Okay, so there's two kinds of poisoning attacks. I think when people say poisoning, they oftentimes just refer to these training-only attacks. So the idea is that at train time, you're going to take an image and you're going to add some sort of adversarial perturbation to it. So now you have this perturbed image, you stick it in the training set, and the perturbation is crafted in such a way that if you train on this data, then at test time, a target image will come along and it will get an adversarial label. So by inserting this poison image into your data set, you basically embed some sort of behavior that is desired by the adversarial agent. And in most papers in the literature, that behavior is that when there's a particular test image that will come along that will then be misclassified. There are also training and testing time attacks. These are often called backdoors or Trojan attacks. And the difference is that these require you to modify both the training and the testing data. And so you might modify the training data by sticking a trigger in it. You might put a star on a bunch of images, for example, and then at test time, you embed that trigger in an image, and that will elicit the desired behavior, right? And so this is a stronger threat model in the sense that it requires you to modify both training and test images, but it's also a more powerful attack in some sense because you can in principle change the label of any image just by inserting a trigger. And one thing I'll point out later, there are also hidden trigger attacks where you're going to modify the training images in such a way that it's not so apparent what the trigger is. Okay, so when I talk about a different kind of poisoning attacks, there's certain properties that they will have, and these are two properties that are often discussed. But there's this clean label property. Clean label, an attack is clean label if the images appear to be labeled correctly by a human. So if someone decided to audit the data and check that all the labels were correct, they wouldn't necessarily notice anything funny, right? The images look like natural images. They appear to be labeled correctly. And a lot of the attacks that I talk about are also targeted, which means that they're only going to change the test time performance of the model on selected target images. And this makes it difficult to detect that poisoning has occurred if those selected images are not in your test set. This is different. Targeted attack is different than what is called an availability attack. An availability attack, the goal is to just degrade model performance on average as much as you possibly can. Availability attacks are frequently studied in the context of classical models like linear regressions and SVMs, whereas targeted attacks that sort of pick and choose different behaviors on different test images, these are usually done using neural networks. And you really need the fluidity of the decision boundary of a neural network in order to make a targeted attack work. Okay, so I'm going to start by reviewing a couple of these different attacks. And in particular, a lot of the early work in this area was done in the field of transfer learning. So we assume that the victim already has a pre-trained model, and they're going to fine-tune that model on a relatively small data set. In this fine-tuning regime, one of the a really useful heuristic that has been used to craft a bunch of different attacks is this collision attack heuristic. And the idea behind the collision attack is that suppose that I have an airplane and I want to create poison frog images, and I'm going to attack this airplane with poison frogs. But one way we could do this is you could start with an unpoisoned feature extractor, and that feature extractor tends to group all the frogs together in Frogville and all the airplanes together in airplane land, right? A feature space tends to be very well structured. So this is a diagram of feature space. And then I'm going to solve an optimization problem that says, take this base image B, this is a frog. That's the base image we're going to start with, and reconstruct a poisoned image X. This is the image we're trying to solve for, in such a way that X lies close to B in pixel space. So to a human, the poisoned image looks like the original frog. And at the same time, in feature space, there's a collision between the poisoned image. So the features extracted from the poisoned image X and the features extracted from this target image, which is an airplane. So you solve this optimization problem and you find an image that looks like a frog to you and me, but in feature space, it lies in exactly the same location as this airplane. And so you fine tune on this data, and neural networks tend to overfit on small data sets. And so when you fine tune, you move the decision boundary to accommodate the fact that there's an image at this location in feature space that is labeled as a frog, right? That came from this base image that's been perturbed. And so now at test time, when this airplane comes along, it lies in exactly the same location. And so it's also classified as a frog, right? And that's called a feature collision. There's a bunch of different variations on feature collisions. For example, you could actually drop a trigger in here, and you could train this image to collide with feature collide with any other image that contains this trigger, right? And if you did that, you could create something like a hidden trigger backdoor attack. So this is using the feature collision heuristic, but to create a poison attack that has a trigger instead of creating an untriggered attack. And there's also a bunch of other variations on this. For example, there are these polytope-based methods. This is something we've worked on in our group, but actually I think the most powerful polytope methods right now are from other teams. The idea behind a polytope method is that instead of trying to collide exactly with the target image, what you'll do is you'll put down basically a polytope of poison images. So you create sort of a cage of poison images that surround the target image. And the idea is that the target image lies inside the polytope mapped out by these poisons. When the decision boundary moves during fine tuning, it generally tends to envelop this entire polytope. So the whole convex hull of this set of poisons tends to get wrapped into a different class. And then that allows you to poison very large regions of space. So this is very useful, for example, if you don't know exactly what feature extractor the victim is using. If you want these kinds of attacks to work in more of a black box setting, they're much more effective if you poison these large regions of space. And in particular, I think this bullseye polytope method is probably one of the most effective poisoning methods right now for fine tuning, where they create one of these polytopes in such a way that the target image lies right in the middle of the polytope. So these kinds of methods tend to be quite effective. So here's just some examples. This is poisoning a fine-tuned Imagenet model. So I'm going to take this original image of a dog, and I'm going to poison it. If I create this poisoned dog, it might look a lot like a regular dog to you and me, but if I stick that one image in the training data set, then the image above it becomes labeled as a dog at test time. If I stick this poison image in, then this fish above it is now labeled as a dog at test time. I can create poisons for all of these fish, and they're usually very difficult to see, especially when you're poisoning high resolution data sets like Imagenet. And just to show I didn't cherry pick too badly, I can flip this problem around and I can poison these fish images to change the label of all of these dogs and make the classifier think that all of these dogs are fish. So this is a really simple and very reliable kind of attack, but it really is focused in the transfer learning scenario. Getting this to work for end-to-end training where you don't have any knowledge of what feature extractor is going to be created is more difficult. And so a lot of work that's been done recently is on looking for ways to push poisoning methods further. So you might look at, particularly we're interested in being able to poison end-to-end training and being able to defend end-to-end training systems. But there's other things you might be interested in, like maybe you want to be able to poison using any base images, right? With feature collision attacks, you're taking frog images and using them to make other test images into frogs, for example. Maybe you want to be able to poison using any base image. Maybe you want to have other attacker objectives other than just misclassification. For example, maybe you want to attack something like fairness. And we also want to know whether these can scale up to industrial systems. Can we get them outside of the lab and get them to work on these large scale complex systems? So here's one of our first attempts to sort of scale things up to more complex systems. This is called Metapoison. The way Metapoison works is we're actually going to simulate the training pipeline of the victim. So the attacker will simulate the training pipeline of the victim and try to directly craft perturbations to training images that will have specific impacts on that pipeline. So here's what happens. The adversary runs a standard SVD training process. They have a big batch of data, and they have a small catalog of poisons that are going to float around in the data set. So you sample a random batch of images. Maybe it contains a poison or two, maybe it doesn't. You're just doing random sampling, just like the victim will do. Then the adversary runs SGDs. So simulate SGD. You start with model parameters, theta. You run SGD using this sampled batch, and that produces updated parameters, theta prime. Then the victim measures how well those updated parameters accomplish the adversarial objective. So this loss is the adversary's loss. It measures whether certain test time images are classified with an adversarial label. So are they classified incorrectly? And then the adversary backprops this entire process. So you backprop through from this adversarial loss through the entire training algorithm back to this image, and you're going to make a gradient update to this poison image so that after you use it for training in SGD, you get an adversarial objective that is low as possible. Because we're backpropping through the training loop, this looks a lot like meta-learning, and that's why we call this framework Metapoison. So Metapoison is really nice because, as an attacker, because it can create attack images that are very difficult to see. So here's 2 columns of CFAR images and then 2 columns of the corresponding poisons. And you'll see that it's very difficult from looking at this clean image and this poison image. It's very difficult to tell that poisoning has happened. But by inserting these very difficult to discern poisons into a data set, we can actually change the label. For example, this bird can be changed into a dog. Another thing about Metapoison is that it tends to be very transferable. So for example, if the attacker is crafting attacks using a ResNet 20, then those attacks work about 72% of the time on a ResNet 20. This is assuming that the attacker can poison 1/10 of 1% of the data. But it actually works even more frequently on VGG, and it works almost as frequently, about 63% of the time, on a simple 4-layer ComNet. So the transferability of these methods in the black box setting actually tends to be much stronger than we've observed for other kinds of attacks. But the interesting question then is how realistic are these sorts of attacks on industrial systems? Could they actually work on realistic systems? And so to test this out, we actually deploy this attack on Google Compute Engine. So Google has an AutoML API where you upload your model, and it will create you upload your data set, it'll create a model for you in an automated way. And I don't know, this is a complete black box. I don't know what optimizer they use. I imagine it's probably a proprietary optimizer. I don't know how they're doing it. They're doing some sort of architecture search, but I don't know how they're doing that architecture search under the hood. I don't know what learning rate schedule they use. I don't know whether they're using momentum and weight decay. I don't know any of these things. But if we upload our poison CFAR data set, we can change this 82% bird into a 69% dog by poisoning about 1/5 of 1% of the data points in CFAR. So then the question is, that we got that to work against an industrial system, but how well will this scale? CFAR is a pretty low resolution data set. For imaging, it's not necessarily very realistic. The question is, can we scale this up to Imagenet? And so we looked at other kinds of methods that are a bit more scalable. So here's one called, it requires a lot less computation than Metapoison, and this we call gradient alignment. So here's the idea behind gradient alignment. What the adversary would like the victim to do is train on the adversary's loss. The adversary has a loss with target images in it and target labels that the adversary wants to be placed on them. And for the adversary, what they'd love to be able to do is get the victim to train on this adversarial loss, right? So what they'd like them to do is start with theta, network parameters, and then march down the gradient of the adversarial loss, because that will lower the adversarial loss function and accomplish the adversarial objective. The adversary can't really make that happen, though, because the victim is not training on the adversarial loss. The victim trains on this loss that is crafted using a data set that contains a range of poisoned and mostly unpoisoned images. So the idea behind gradient alignment is that the adversary is going to look at the training gradient. Let's look at this natural gradient using natural images, so not poison. And what we're going to do is we're going to make a small perturbation to a subset of these images. And we want to make that perturbation delta in such a way that we align this natural training objective with the gradient of the natural training objective with the gradient of the adversarial objective. So we have this, we want to maximize the correlation between the adversarial gradient for a value of theta and the natural gradient for a particular value of theta. And we do that by optimizing delta, this perturbation to the images. So you want to find a small perturbation of training data that has the effect that now this natural gradient that the victim is going to use is highly correlated with the adversarial gradient. If you can accomplish this, if you can make this correlation large, then doing gradient descent on the natural data set is going to have the same effects as if you were optimizing the adversarial objective rather than this natural objective. And it turns out that from a computational standpoint, it's much cheaper to optimize this correlation than it is to do the original meta-learning, the original Metapoison attack. And as a result, we're able to scale this up to Imagenet. So here's an example. This is also poisoning Google AutoML. This does not work 100% of the time. So what we did is we uploaded this data set to Google AutoML 5 times. And one of those times our poisoning attack was successful using 1/10 of 1% of the data, we randomly chose images, but this otter ended up being changed into a dog with our attack. Now, I think we could probably optimize this further to get higher levels of success, but these experiments are quite costly. It costs about $1,000 to train Imagenet from scratch on AutoML, and so we're not really willing to run hundreds of experiments to try to fine-tune this behavior. But I think it's at least an interesting demonstration that these sorts of attacks can work against commercial APIs. Another thing that I'll mention is that this isn't just for untriggered attacks. You can do this for triggered attacks as well. So here's an example of using gradient alignment to craft a triggered attack. So here's a clean image and its corresponding poisoned ImageNet image. And then here's a target image we want to change the label of, and we can change its label by inserting this trigger patch into it. And we can accomplish the same sort of attack using gradient alignment in both the triggered and untriggered setting. Okay, so I'm just going to say a few things real quickly about defenses. Now, defenses, just like attacks, is also quite a wide area, and there's a lot of different defenses, and this is an area that also is rapidly evolving. I think things are changing quite quickly in this area, and I think that they should be rapidly evolving. I don't think that the defenses we have really stand up really very well at all to state-of-the-art attacks. But there's a range of different attacks that are out there. For example, there's a Steinhardt 2017 paper that tries to detect image outliers. And this is particularly effective for lower dimensional data sets, but it could be used on images as well. In images, I think it's generally considered more effective to try to identify image outliers in latent space. So the idea behind these attacks is that poisoned images are probably going to lie in strange locations in feature space. If you use a feature collision attack, that's probably true. You take a frog image and you're going to poison it to lie in airplane space. And so you might have frog images that are in latent space that might be outliers with respect to the rest of their class. And so you can try to prune those outliers. And I think that these kinds of attacks or these kind of defenses are effective against simple feature collision based attacks. But actually, in our research, we've shown that this doesn't really work well against more direct, like meta learning or gradient alignment types of attacks, where you can actually craft poison images that are not outliers from their class in feature space. There's also a range of really interesting methods for identifying when models have been poisoned. And when I first read about this line of research, I was a little skeptical of it, but actually it seems like these methods work quite well, and some of them are quite effective at identifying poisons, even when there's a range of different poisoning methods that have been used. And then there's also these certified methods, which I think are quite interesting. There are methods using Gaussian smoothing, and there are methods that use differential privacy in order to get robustness against poisoning. I think all of these are really interesting. One particular direction that I've been interested in recently is taking the adversarial training framework, which is a state of the art for defending against adversarial attacks. In fact, it's considered to be one of the only really strong frameworks for defending against adversarial attacks. The question is, can you take this adversarial training framework that is used to defend against evasion attacks and repurpose it to defend against poisoning? And so we've been looking at what we call adversarial poisoning instead of adversarial training. And here's the idea. In adversarial training, you inject adversarial attacks into the training set with the idea that by doing so, you create a classifier that is immune to adversarial attacks. In adversarial poisoning, we're going to do something very closely related. Instead of injecting adversarial attack images, we're going to inject poisoned images into the training set, and we're going to train the network to be immune to those poisoned images. So it's sort of like directly porting this adversarial training idea, but using it to defend against poisoning rather than using it to defend against evasion attacks. So here's how this kind of defense would work. So the defender, the potential victim, is going to basically simulate a poisoning process at train time and then try to deflect it. So every training batch is going to contain two kinds of images. We'll sample some regular training images like this frog, and we'll sample some target images like this airplane. And then here's what happens. So on stage one of training, the defender is going to do a forward pass using this frog image. So you pass this image, go back a little bit, you pass this image into SGD, you update your model parameters, right? And then the victim will And then the defender will measure the accuracy of the classifier, but the accuracy is going to be measured on this other image, this target image that was sampled. So half of the batch are these poison images, half are the target images. The victim does a forward pass on these poison images and then evaluates the accuracy on the target images. Then the defender backprops through that training process and creates a poisoned image that tries to change the label of this airplane. So now we have a poison frog that tries to change the label of this airplane. So that was stage one. In stage one, we sample 2 batches of images, the poisons and the targets, and then we update the poison images so that they are poisons for changing the label of the targets. Then on stage 2, which is a training stage, you put both of these images together into a big batch and you do a forward and a backward pass and you train on them. So the idea is that the network now gets to see the poisons and the targets at the same time, but these targets, it knows what the correct labels will be, and then we get to update the model parameters so that even in the face of these poisons, even when poisons are in the batch, it still assigns the correct labels to these target images. So there's a whole bunch of different defenses that we have studied and implemented, and they all have their pros and cons. You know, and it's nice to, everyone likes to publish papers and say that they're the state of the art and they're the best in some way, but the truth is there's sort of a Pareto frontier of different attacks. So this is looking at average poison success on one axis and validation error on the other axis. You can always deflect all poisoning attacks just by not training your model, right? You could just start with random parameters and never train them, and poisoning becomes impossible, right? But then your validation error is going to be very low, right? And at the same time, you could do nothing to defend against poisons. You might get very high validation error on natural images, but the poison success rate might be quite high. And so there's really a Pareto frontier. There's sort of a trade-off that you can make between these two. And what we find is that these adversarial poisoning methods are quite effective. They definitely seem to be on this Pareto frontier, and they manage to be, at least among the things we've tested, they manage to get the lowest average poison success. But like I said, there are other things you might care about, like validation accuracy, and there are even other defenses, like we find this training with cut mix plus Gaussian noise, for example, is also basically on this Pareto frontier, right? It doesn't suppress average poisoning success as much as something like adversarial poisoning, but it does manage to preserve a lot of validation accuracy. And then one thing I'll also point out here is there's this green line here. These are differential privacy based defenses, and they have their own, sort of Pareto frontier. We've done some work recently on new kinds of mix-up based defenses. Like we have a defense called DP Insta-Hide that can sort of break through this Pareto frontier a bit and allow differential privacy defenses to perform better, but they still don't perform quite as well as these more heuristic defenses. I think that this differential privacy-based defense area is really interesting because differential privacy defenses come with certifiable guarantees. And so if we can continue to improve the performance of these differential privacy methods, I think that will be really good progress for the field. Okay, so one last thing I just wanted to mention is if you're interested in studying poisoning attacks, my student, Avi Schwarzschild, created this benchmark, just how toxic is data poisoning. And the idea is that he wants to benchmark the effectiveness of different poison attacks in different settings, like a white box setting, a black box setting, and an end-to-end training scenario. And one of the reasons why we created this benchmark is just because we found that different attacks we're really evaluating in the literature, evaluating in completely different scenarios. So you can use different epsilons for how much an image can be perturbed. You can use different percentages of the data set to be poisoned. You could poison 0.1%, you could poison 1%, you could poison 10%. And so there wasn't really any consistency among the kind of threat models that people were using in the literature. And so to actually compare the effectiveness of these different kinds of attacks, what we did is we created this benchmark where there's a standard toolkit for training. It sort of standardizes all of these test scenarios and allows you to quantify the effectiveness of different attacks in a fairly precise way so that we can actually compare these different attacks a bit better. All right, and finally, I just want to say thank you for taking the time to listen. And I spoke about a bunch of different works on my group and others, but in particular, I just want to say thank you to my co-authors that worked with us on this review article on poisoning. This is a project that was led by Michael Goldblum, who's been a postdoc in my lab, and he's moving to NYU at the end of the summer. We're sad to see him go. And then Dimitris Tsipras, Qilin Qi, Jinyun Chen, and Avi Schwarzschild. These folks really led this project, and I think they did a terrific job. And I also want to thank my faculty co-authors, Don Sung, Alex Madri, Bo Lee. They were also fairly involved in this workshop. So thank you to everybody, and thanks for inviting me.
Hello.
Yes.
Thanks for your great talk. And I have a question about the adversarial poisoning method. You mentioned that we can add some poisons to the training data, and then we can use this as a data augmentation method to make the model immune to the poisoning attack. I have a question. There are many types of triggers: pixel trigger, pattern trigger, clean label, backdoor attack. So how can we make the poisons in the training data so that we can defend all types of backdoor attack?
Yeah, so one of the difficulties here is just like in the adversarial training scenario, there's this problem where you can if it's on evasion attacks as well, you can adversarially train against one modality, one kind of attack, and that doesn't necessarily guarantee success against a different kind of attack. So, adversarial training against L2 bounded attacks doesn't make your network immune to some sort of semantic attack, for example. And there is, what we found is just like in the adversarial training literature, there is crossover, right? So if you robustify against one threat model, you gain robustness against another, but you don't gain as much robustness as if you had trained against that threat model specifically. And we do look at these crossover attacks, and we do look at adaptive attacks also that specifically try to attack this adversarial poisoning method in our paper. What doesn't kill you makes you robuster, and we do find that the effectiveness is lower when you test on an attack that is different than what you trained on, but still some of the robustness remains. So I think in that sense it's comparable to what you might observe for attack crossover and adversarial training.
Okay, thanks for your answer.
Okay, any other questions?
I can't see I think there might be some things in the chat, but I can't actually see them with my screen shared. So feel free to chime up if there's anything else anyone would like to ask.
Yeah, if you have,
thanks for the great talk. I have a question related to the adversarial trigger.
Mm-hmm.
So my question is that trigger universal across all the images? And I'm still a little confused on how is that different from adversarial patch or mask PGD?
How is it different than an adversarial patch? So these are okay. These are all closely. Almost everything that happens in the adversarial training literature has sort of an analog in the poisoning literature. So it is the trigger. The trigger is very closely related to an adversarial patch, right? So in the adversarial training setting, there are patch attacks where you try to do. When you say adversarial patch, I usually associate that language with a test time attack, so an evasion attack. And this is essentially doing the same thing, but in the poisoning scenario. So it's basically an adversarial patch that causes a particular bad behavior. Okay, so how is it different? The difference is that it's a stronger, an adversarial patch threat model, you do not have the ability to manipulate the training data. Whereas in the poisoning scenario, you do. So with the simplest kind of triggering attack, for example, you might take a bunch of Boba Fett images and put a little star on them and put those into the training data set. And then the neural network will learn that that star is something that appears in a Boba Fett image, and then you can put that star in any image at test time and it will become Boba Fett, right? So there are ways to do backdoors and Trojans that are more agnostic to the architecture. So for example, that simple process I just described only depends on manipulating the data set. It doesn't depend on it doesn't even use information about the neural architecture, the optimizer, or anything else, right? And so it's a much more powerful attack if you allow the adversary to have access to the training data as well as the test data, you can create much more powerful patch attacks than if you only have access to the test data. But I would say, once the model's already been trained, from the attacker's perspective, it's sort of the same as a patch attack, right? You have a patch that you're going to insert to change the model behavior. It's just that if you can poison, you can be a little bit more certain about the behaviors you're going to get at test time.
Okay, I see. So is that trigger universal across images?
It is.
And also,
yeah, there's a lot of different kinds of trigger attacks, but most papers that study this, it is universal. It is universal.
And also universal across training and test?
Across training and test.
So during is that pattern, trigger pattern universal in the training data and also the same in tested?
Oh, you're saying, is it, I would say, so there are methods that will try to like regenerate patches at test time that are customized for a particular image, but by and large, they craft a universal patch. Then you poison all the images with a trigger, which might look like a patch, and then you test with the exact same patch. So I think that's what you're asking, right? It is universal in the sense you use the same patch for training and testing. And there are methods where the attacker chooses what that trigger is. So it could actually be something like a star. It could be a weird pair of sunglasses or a piece of jewelry that you wear. And then there are also methods where you craft, you use optimization to basically craft an optimal trigger. So you'll learn a patch that is an optimal attack, right? And now you could do that without manipulating the data at train time. You can learn an optimal patch just to attack a model at test time. But these sorts of methods will also exploit the train time behavior. And they'll learn an optimal patch for poisoning that is also effective at test time. So it's just a way of boosting the effectiveness of that patch attack. And but yeah, to answer your question, it is universal across both, usually.
Okay, yeah, thanks for the explanation.
Great. We got one last question from the chat. The question is, could you provide a little bit more about how the loss function and the gradient can help the model to identify the poisoning?
How the loss function, you mean is this a question about defending against poisoning? Which I believe it is. Well, It sounds like they're asked, so how can the loss function and the gradient be used to defend against poisoning? Maybe I'll say, so I don't know that there's any works that that are quite as straightforward as, and I could be wrong about this. I don't think there's anything that's quite as straightforward as looking at the loss function and the gradient alone. There are works though that detect, so let me go to some of these detection-based defenses. There's a bunch of work now on methods for detecting when your model is poisoned. And there are works for actually trying to fix those models. So things like Deep Inspect, like NeuroCleanse, this Tabor, MNTD, these sorts of defenses. And one thing that they'll do, so here's like one particular approach, is you can actually create, you can learn images whose test time labels tell you about whether the model has been poisoned. So for example, you can learn an image, it'll be like a weird looking pattern, but you can learn an image that has the property that it gets one label when you show that image to a poisoned model, and it gets a different label when you show it to an unpoisoned model. And these are the kinds of defenses that I said, to me, it's quite amazing that you can create an image like that. It's a little bit unintuitive to me that would work, but actually empirically, these methods seem to work quite well. And I think maybe there still needs to be some more work done on studying how these methods work across really diverse types of poisoning attacks. How effective are they at detecting, really different kinds of poisoning attacks? Maybe things that the defender isn't aware of when they create that image. But so far, it seems like a lot of these defenses actually work quite well. Even across different types of poisons. But that's the most effective, that's one of the most effective ways that has been presented for detecting poisons using sort of an optimization framework.
Okay, great. Thanks for your talk, and it's a very nice overview of the poison attack. And you may stop sharing your screen so we can move to the next one. Thanks, Tom.
Thank you very much. Thanks for having me.